Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 5.3 on diagonalization. I'll teach you all about how to diagonalize a matrix and how to easily raise a matrix to a power. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Before we walk through example problems, I want to highlight the main purposes for diagonalizing a matrix. Diagonalizing a matrix is a powerful technique in linear algebra that simplifies calculations and helps us understand a matrix structure. The main purposes of diagonalizing a matrix are simplifying the process of raising a matrix to a power. Instead of multiplying a matrix repeatedly, we can easily raise the diagonalized form to a power. Diagonalizing a matrix also helps when analyzing differential equations and discrete dynamical systems. It helps us understand stability and long-term behavior. Diagonalizing a matrix also decouples linear transformations. Transformations can be separated into independent components along its eigenvector directions. Diagonalization also helps us identify matrix properties. The eigenvalues of a diagonal matrix reveal key properties such as determinant and rank. Before we can diagonalize a matrix, we need to know if it can be diagonalized and what the structure of a diagonalized matrix looks like. The Diagonalization Theorem provides us with all this information. An n by n matrix A is diagonalizable if and only if either one of the following are true. 1, A has n distinct eigenvalues, and or 2, A has n linearly independent eigenvectors. If A has n linearly independent eigenvectors, the sum of the dimensions of the eigenspaces is going to equal n. Let me give you an example. If A is a 3 by 3 matrix, and it has 3 distinct eigenvalues, then the matrix is diagonalizable. If it doesn't have 3 distinct eigenvalues, then it still may be diagonalizable. You have to then check if it has 3 linearly independent eigenvectors. If it does, then it's diagonalizable. We'll do some examples in a minute that will help us understand this better. It's also important to note that if a matrix has n distinct eigenvalues, like step 1, it will have n linearly independent eigenvectors. This means if step 1 is true, then step 2 is going to be true. However, if a matrix has n linearly independent eigenvectors, it may or may not have n distinct eigenvalues. This means that if step 2 above is true, 1 may or may not be true. There's so much theory that goes along with linear algebra. We're now going to shift gears and we're going to look at the structure of a diagonalized matrix. If a square matrix A is diagonalizable, we can express it as A is equal to PD times P inverse. P is a matrix whose columns are the eigenvectors of A, and then D is a diagonal matrix with the eigenvalues of A on its diagonal. Let me show you what P and D look like for a 3 by 3 matrix that has 3 distinct eigenvalues. Our diagonal matrix D is going to have the eigenvalues of matrix A along its diagonal. And then because it's a diagonal matrix, all the other entries are going to be equal to 0. And then our matrix P is going to contain the eigenvectors corresponding to each of the eigenvalues of matrix A. P is going to look like V1, V2, and V3. It's important to note that the eigenvalues and their corresponding eigenvectors all have to be in the same respective columns. If eigenvalue 1 is in column 1, then eigenvector 1 has to be in column 1. Likewise, if eigenvalue 2 is in column 2, eigenvector 2 is in column 2. And then if eigenvalue 3 is in column 3, then eigenvector 3 has to be in column 3. Let's now walk through some example problems. In our first example, we're given 2x2 matrices and asked to determine if the matrix is diagonalizable. The first thing we need to check is to see if the matrix has 2 distinct eigenvalues. Our matrix is an upper triangular matrix, so the eigenvalues are just the entries along the diagonal. So we can write down that lambda is equal to 3 and minus 1. We have a 2x2 matrix and we have 2 distinct eigenvalues. So we can say that yes, our matrix is diagonalizable. Let's look at part B. This matrix is also an upper triangular matrix. So we can see that lambda is equal to 3 and 3. Our matrix is a 2x2 matrix, and we don't have 2 distinct eigenvalues. Instead, we have 1 repeated eigenvalue. So our matrix may or may not be diagonalizable. What we have to do now is check to see how many eigenvectors it has. An eigenvector is the solution that we obtain from augmenting a minus lambda I with 0, and then putting this in reduced echelon form. The number of linearly independent eigenvectors is going to be equal to the number of free variables in a minus lambda I. To find the number of eigenvectors, we actually don't have to find them. We just have to find the number of free variables in this matrix. Let's go ahead and compute this matrix. This is 3 minus lambda, 2, 0, and then 3 minus lambda. We're going to plug in that lambda is equal to 3. So this is 0, 2, 0, 0. And then we'll go ahead and we'll circle our pivot. And then we'll notice that our first column is a column without a pivot. So that tells us that we have 1 free variable. That means that we're going to have 1 linearly independent eigenvector. Since we have a 2x2 matrix, our matrix is only going to be diagonalizable if we have 2 linearly independent eigenvectors. So the answer to this question is going to be no. Our matrix is not diagonalizable because we don't have enough linearly independent eigenvectors. Let's now look at our second example. We're given a matrix A that is factored in the form PD P inverse. We're asked to find the eigenvalues of A and then find a basis for each eigenspace. The point of this problem is to see if you understand the structure of a diagonalized matrix. Let's begin by writing down our formula. A is equal to P, D, P inverse. And then we'll mark these matrices as P, D, and P inverse. Let's first find the eigenvalues of A. The eigenvalues of A are going to be the entries along the diagonal of matrix D. Our eigenvalues lambda are going to be 1, 1, and 5. Let's now find a basis for each eigenspace. We're going to have an eigenspace for each distinct eigenvalue. We have 2 distinct eigenvalues, 1 and 5, so we're going to have 2 eigenspaces. The basis for the eigenspace corresponding to lambda is equal to 5 is going to be the eigenvector in P that's in the same corresponding column as our eigenvalue 5. So we can say that our basis contains this vector, 2, 2, 2. Let's now find the basis for our eigenvalue lambda is equal to 1. This eigenvalue is located in the second and third columns of D, which means its eigenvectors are going to be located in the second and third columns of P. Our basis then is just going to contain these 2 vectors. Vector 2, 0, minus 1, and then vector 2, minus 2, 0. The reason that this matrix is diagonalizable is because it has 3 linearly independent eigenvectors, and the dimension of our eigenspaces is equal to 1 and 2, and they add up to be equal to to 3. And our matrix is a 3 by 3 matrix. Let's now look at example 3. We're given that A is a 3 by 3 matrix with 2 eigenvalues. That means one of the eigenvalues is a repeated eigenvalue because we'll have a total of 3 eigenvalues. We're then told that each eigenspace is one-dimensional, and then we're asked, is A diagonalizable? If a matrix is diagonalizable, the sum of the dimension of the eigenspaces must equal n, the number of rows and columns of matrix A. Since our matrix in this example is a 3 by 3 matrix, the sum of the dimensions of the eigenspaces must equal 3. In our problem, we have 2 eigenvalues, so that means we're going to have 2 eigenspaces. And then each eigenspace is one-dimensional. So that means that the total dimension of our eigenspaces is going to be 2 times 1, which is just 2. But we need the total dimension of our eigenspaces to add up to 3. Because our dimensions only add up to 2, the answer to this is no, A is not diagonalizable. Let's now learn how to easily compute the power of a matrix. If A is a diagonalizable matrix, it can be easily raised to a power. I'll show you exactly how this works. We're going to start with our definition of a diagonalizable matrix. A is equal to P times D times P inverse. And I'm going to show you what A squared looks like. A squared is going to be PD P inverse times PD P inverse. And we can combine this because P inverse times P is our identity matrix. And we end up with just P D squared P inverse. So when we compute A squared, all we have to do is square our diagonal matrix. The formula for A raised to a power k has the same structure as this formula for A squared. A to the k can be written as P times D to the k times P inverse. So all you have to do is just raise your diagonal matrix D to the power of k. Let's now get some practice with computing powers of a diagonal matrix. We're given a 2 by 2 matrix D, and we're asked to compute D squared, D cubed, and then D to the k. Let's begin by computing D squared. D squared is just our matrix D times our matrix D. And we just have to multiply these out. And we end up with 2 squared. I'm going to write it like that instead of writing down a 4. And then we get 3 squared. Now we can go ahead and write it down as 4009. Let's now compute D cubed. So our D cubed is just going to be D times D squared. We have 2003, and then I'm going to use the form of D squared that has a 2 squared, a 0, 0, and a 3 squared in it. This way we can see the formula a little bit easier. When we multiply these two matrices, we end up with a 2 cubed, a 0, 0, and then a 3 cubed. And then we can go ahead and write down what that is. So this is going to be an 8, 0, 0, and 27. Using the same structure, we can see that D to the k is going to be just like this matrix D cubed, except now instead of a 3, we're going to have a k, and we have 2 to the k, 0, 0, and then 3 to the k. If D is a 3 by 3 matrix with 3 eigenvalues, lambda 1, lambda 2, and lambda 3, then D to the k is going to look like this matrix, and all we have to do is just raise the diagonal entries, which are our eigenvalues, to the power of k. That's so much easier than having to multiply a matrix by itself k times. Let's now see how we can raise a matrix to a power of k when our matrix is written as P times D times P inverse. Let's begin by writing down that our A is equal to PD P inverse, and then our A to the k is equal to P times D to the k times P inverse. We'll now plug in our matrices that are above. We have P, 1, 2, 0, 1, and then we have D to the K. And remember, all we have to do to find D to the K is just raise our diagonal entries to the power of K. And then we have P inverse. All we have to do now is just multiply everything out. I'm going to multiply these two matrices first. We get A to the K in our first entry. And then in our second entry, we get 2 times B to the K. The entry in the lower left is going to be 0. And then the entry in the lower right is going to be B to the K. And then this multiplies our third matrix, 1, minus 2, 0, 1. Now we just have to multiply these two matrices. Our upper left entry is going to be A to the K. And then our upper right entry is going to have two terms in it. And it's going to be minus 2A to the K plus 2 times B to the K. In the lower left, we're going to get a 0. And then in the lower right, we're going to get a B to the K. We can simplify the term in the upper right, and we can write this as A to the K, and then pull out a 2, and we have B to the K minus A to the K. And then in the second row, we have a 0 and a B to the K. And this is our final matrix. Let's now look at our second example, where we're given a matrix P and D, and we're asked to compute A to the fourth. Just like we did for our first example, we're going to begin by writing matrix A as P times D times P inverse. And then we can write A to the fourth as P times D to the fourth times P inverse. Before we put everything together, let's first compute matrix D to the fourth. That's going to be our matrix D with our diagonal entries raised to the fourth power. And this is equal to the matrix 1 over 16, 0, 0, and 1. The other thing what we need to do before we multiply everything out is to compute P inverse. So this is the inverse of a 2 by 2 matrix. It's equal to 1 divided by the determinant, which is 5 minus a negative 2 times a negative 2. It's just the main diagonal entries multiplied minus the off diagonal entries multiplied. And then our matrix has the diagonal entries switched, and then the off diagonal entries get a negative. 5 minus the negative 2 times the negative 2 is just 1, which is really nice. Our matrix P inverse is just then 5, 2, 2, 1. Now we can go ahead and use our formula that I just highlighted to compute A to the fourth. We're going to have our matrix P, 1 minus 2 minus 2, 5, times our matrix D to the fourth, which is 1 over 16, 0, 0, 1, and then our P inverse, which we found to be 5, 2, 2, 1. Now all we have to do is multiply all of this out. I'm going to multiply these two matrices first. So we're going to get a 1 over 16, and then we're going to get a minus 2. In the lower left, we're going to get a minus 2 over 16, and then in the lower right, we're going to get a 5. Now we're going to take this matrix, and we're going to multiply it by 5, 2, 2, 1. In the upper left, we're going to get a 5 over 16 minus 4. And then in the upper right, we're going to get 2 over 16 minus 2. In the lower left, we're going to get a minus 10 over 16 plus 10. And then in the lower right, we're going to get a minus 4 over 16 plus 5. Let's see what this gives us. We got some fractions here that we have to work with. The upper left is going to be 5 over 16 minus 64 over 16. The upper right is going to be 2 over 16 minus 32 over 16. The lower left, we have a minus 10 over 16 plus oh wow, 160 divided by 16. And then in the lower right, we have our minus 4 over 16 plus 5 times 16, which is going to be 80, divided by 16. Let's now combine our fractions. 5 minus 64 is a minus 59 over 16. 2 over 16 minus 32 over 16 is a minus 30 over 16. In the lower left, we're going to get 150 over 16. And then in the lower right, we're going to get a 76 over 16. Now, you may be able to go ahead and leave your answer like that, but I always like my students to reduce the fractions as much as they can. So if we do that, the minus 59 over 16 can't be reduced, so that stays. The minus 30 over 16 can be reduced to minus 15 over 8. Our 150 over 16 can be reduced to 75 over 8. And then in the lower right, we can reduce that to all the way down to 19 over 4. This answer that we got then is just our matrix A raised to the 4th power. Now that we know how to compute the powers of a diagonal matrix, we can learn how to diagonalize a matrix. If A is a diagonalizable matrix, we can diagonalize it by writing it as A is equal to PD times P inverse, or finding P and D. This process is rather lengthy, so I wrote down steps that we can follow to diagonalize a matrix. The first step is to find the eigenvalues of matrix A and construct our diagonal matrix D. We can do this by solving the determinant of A minus lambda I is equal to 0. Our second step will be to find the eigenvectors of matrix A and construct matrix P. To do this, for each eigenvalue, we need to construct A minus lambda I augmented with 0 and then solve for vector x. And that's going to give us the eigenvectors. Let's now walk through 3 example problems where we're going to diagonalize a matrix, if possible, by finding matrix D and matrix P. In our first example, we have a 2x2 matrix. Our first step is to find the eigenvalues. So we'll take determinant A minus lambda I, and we'll set it equal to 0. We have a 3 minus lambda, a 1, a minus 2, and a minus lambda. And that's equal to 3 minus lambda times minus lambda minus a negative 2. And we set that equal to 0. Multiplying everything out, we get a lambda squared minus 3 lambda plus 2. We can factor this as lambda minus 2 times lambda minus 1. And that's going to give us eigenvalues lambda is equal to 1 and 2. I'm going to assign these eigenvalues to be lambda 1 is equal to 2, and then lambda 2 is equal to 1. In some applications, you always want to make lambda 1 equal to the largest eigenvalue, which is actually called the dominant eigenvalue. Notice that we have 2 distinct eigenvalues, so that tells us that our matrix A is diagonalizable. Now we have to go to step 2, and for each eigenvalue, we have to find a corresponding eigenvector. We'll start with lambda 1 is equal to 2, and we're going to take A minus lambda I, augment it with 0, and we're going to have to reduce it all the way to reduced echelon form. Here we go. We're going to take our matrix A, and we're going to subtract 2 off the diagonal and augment it with 0. This is equal to 1, 1, minus 2, and minus 2. You can see that our second row is a repeat of the first row, so that row is going to go to 0. And our matrix in reduced echelon form looks like this. We'll circle our pivot, and then we'll go ahead and we'll solve for x1. Our x1 is going to be equal to minus x2, so we can write our vector x as x1, x2, and then plug in for x1. So we get minus x2, x2. We can now pull the x2 out, and we're left with a vector minus 1, 1. To find an eigenvector, we need to choose a value for our free variable, and I'm going to choose x2 to be negative 1, just so that the first entry in our eigenvector is positive. I'm going to call our eigenvector v1, and it's just going to be equal to then 1 minus 1. That's what we get when we plug in that x2 is negative 1. I'm going to go ahead and highlight this so that we can find it when we have to write our matrix P. Now we're going to find the eigenvector corresponding to lambda 2 is equal to 1. We're going to do the same thing. We're going to take a minus lambda I, augment it with 0, and put it in reduced echelon form. We're going to subtract 1 off the main diagonal elements of our matrix A. So we have 3 minus 1, 1 minus 2, and minus 1. We'll augment it with 0, and then let's go ahead and see what this gives us. We have a 2, a 1, a minus 2, and a minus 1. It's really nice that our second row is a repeat of our first row, so that row is going to go to 0. And then let's go ahead at the same time and let's divide row 1 by 2. So we end up with a 1, 1 half, 0, 0, 0, 0. This gives us that x1 is minus 1 half x2. We'll come over here and we'll write our vector x as x1, x2. Plug in for x1. We have a minus 1 half x2, x2. We'll pull the x2 out, and then we have the vector minus 1 half 1. Now we'll choose a value for x2. I'm going to choose x2 to be minus 2. This is going to give us a nice eigenvector, which is equal to 1 minus 2. Now we can go ahead and we can construct D and we can construct P. Our matrix D is going to contain our eigenvalues along the diagonal. I'm going to put lambda 1 in the upper left, so this is going to be a 2, 0, 0, 1. And then our matrix P is going to have our eigenvectors in it. We had lambda 1 in the first column, so we have to have v1 in the first column. And this is 1 minus 1. And then our v2 is 1 minus 2. Linear algebra often has some really nice built-in checks, and one nice built-in check that you can do is you can check your answer by making sure that A is equal to P times D times P inverse, or a little bit easier, if you don't want to find P inverse, you can check to see that A times P is equal to P times D, and I got that just by multiplying this equation by P on the right. In our second example, we have a 3 by 3 matrix. We'll begin by finding the eigenvalues of matrix A. We'll compute determinant A minus lambda I and set it equal to 0. We have a 2 minus lambda, 1, 0, 0, 3 minus lambda, 0, and then minus 2, 2, and 3 minus lambda. Looking at this determinant, it looks like it's going to be best to evaluate it if we do a cofactor expansion down the second column. Let's go ahead and put our plus minus. This is a plus, minus, and a plus. Now we can go ahead and evaluate it. We have 3 minus lambda, and now let's cross out the row and column common to 3 minus lambda, and you can see that we're just going to end up with a 2 minus lambda times a 3 minus lambda, and then the other entry is going to be 0. We set this equal to 0, and we end up with lambda is equal to 2, 3, and 3. I'm going to go ahead and label our eigenvalues as lambda 1 is equal to 3, lambda 2 is equal to 3, and then lambda 3 is equal to 2. Now let's do our second step. What we're going to do is we're going to find an eigenvector corresponding to each of these two distinct eigenvalues. So we'll start with lambda 1 is equal to 3. We're going to augment A minus lambda I with 0 and put it in reduced echelon form. Looking up at the top, we have our matrix A, and we're going to subtract 3 off the diagonal entries. This gives us a -1, 0, -2, 1, 0, 2, and then 0, 0, 0. And we augment that with 0. We can see that our second row is a duplicate of our first row, so it's going to go to 0. And then let's go ahead and let's multiply our first row by -1. So we get 1, 0, 2, 0, 0, 0. And then our right-hand side has zeros on it. Let's circle our pivot, and that tells us that x1 is equal to -2 x3, and then x2 and x3 are our free variables. We have 2 free variables, so that tells us that we're going to have 2 vectors in our eigenspace for lambda 1 is equal to 3. Our vectors x are going to be x1, x2, and x3. We'll plug in that x1 is -2x3, and then x2 and x3 go in as themselves because they're free variables. Now we're going to separate everything. We're going to pull out an x2, and that multiplies vector 1, 0, 1. And then we're going to pull out an x3, and that multiplies vector -2, 0, 1. Now we need to choose values for our free variables. I'm going to choose x2 to be equal to 1, and I'm going to choose x3 is equal to -1, just so that our first entry is positive. Our first eigenvector, v1, will then be our vector 0, 1, 0, and our second eigenvector, v2, is going to be our vector 2, 0, -1. I'm going to highlight these because we're going to need to refer back to them when we write our matrix P. Hang with me, we just have one more eigenvector to find. We're going to find the eigenvector corresponding to lambda 3 is equal to 2. We're going to take our matrix and we're going to subtract 2 off the main diagonal. This is going to give us a 0, 0, -2, a 1, 1, 2, and then a 0, 0, 1. And we'll augment it with 0. I'm going to take row 2 and I'm going to switch it with row 1. That way we have a 1 in the upper left-hand corner. And then you might notice that rows 2 and 3 are duplicates of each other. So our third row is going to go to 0. And then I'm going to take our second row and I'm going to divide it by -2. So we have a 1, 1, 2, 0, 0, 1, 0, 0, 0, and we'll augment it with 0. Let's circle our pivots. And then we see that we have to do one more reduction step, and we have to make that entry equal to 0. To do that, we're going to take row 1 and replace it with row 1 -2 row 2. And that's going to give us the matrix 1, 1, 0, 0, 0, 1, and then 0, 0, 0. Let's go ahead and let's circle our pivots again. Our x1 is equal to -x2, and then our x3 is equal to 0. And let's write that x2 is our free variable. Because we have one free variable, we're going to get one vector in our eigenspace corresponding to lambda 3 is equal to 2. Our vector, x, is going to be x1, x2, x3. We're going to plug in that x1 is -x2. x2 goes in as itself, and then x3 is equal to 0. And let's see if we can squish it in. This is x2 times a vector -1, 1, 0. The last thing we need to do is pick a value for x2. I'm going to let x2 be -1 so that this entry is positive. And that gives us our eigenvector v3 is equal to 1, minus 1, 0. Okay, we're almost done. Now all we have to do is create our matrix D and our matrix P. So our matrix D has our eigenvalues lambda 1, lambda 2, and lambda 3. Let's go back up here and find those. They are right here, and they're 3, 3, 2. So on the diagonal, we're going to put 3, 3, and 2. And then everything else is 0. And then we have our matrix P, and that's going to contain our V1, which is 0, 1, 0, our V2, 2, 0, minus 1, and our V3, 1, minus 1, 0. We did it. We got through that problem. I always tell my students that this is probably one of the longest problems you'll do in linear algebra. Hang with me. We have one more example, and it's really important because it's going to be an example where we actually can't diagonalize a matrix. This last example is an example where we can't diagonalize a matrix, and we're given a 3 by 3 matrix. I tried to make this example easier because I chose a upper triangular matrix, so we can just read off the eigenvalues from the main diagonal. So that's our first step to write down our eigenvalues. So we're going to write down lambda 1 is equal to 4, lambda 2 is 2, and then lambda 3 is also 2. We do not have 3 distinct eigenvalues, so our matrix is only going to be diagonalizable if we have 3 linearly independent eigenvectors. Let's see if we have that. Normally, I would start with lambda 1, but here I'm going to start with lambda 2 because it's a repeated eigenvalue, and if we end up not having enough eigenvectors, it's going to come from an eigenvalue that's a repeated eigenvalue. We'll write down lambda 2 is equal to 2, and then we'll take a minus lambda I, augment it with 0, and we'll see if we have enough eigenvectors. Our lambda is equal to 2, so we're going to subtract 2 off the main diagonal. This gives us 0, 4, 6, 0, 0, 2, and then 0, 0, 4 minus 2, which is 2. And we augment this with 0. We have a repeated row, so that row is going to go to 0. Let's go ahead and let's take row 1 and divide it by 4. And then let's take row 2 and divide it by 2. So we're kind of going to do 3 things at once. This gives us a 0, 1, 3 halves, a 0, 0, 1, and a 0, 0, 0. Let's circle our pivots. Before we go on and reduce this further, let's notice that x1 is our free variable. We only have one free variable, so that's going to tell us that we're going to get one eigenvector. Because we have 2 eigenvalues equal to 2, in order to diagonalize A, we would need to have 2 eigenvectors. So we can actually stop right here, and we can say that A is not diagonalizable. That's why it's always nice to know that the number of free variables in A minus lambda I is going to equal the number of eigenvectors that you can get. Thanks for hanging with me. We got through all of this material. Be sure to check out the next video in this series where I'll teach you all about orthogonality.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.